All right, so we're here for chapter 4 notes today. And again, this chapter is covering the energy of life, about 38 slides to this one. So as we get started here, I wanted to point out that this is the start of Unit 2, and Unit 2 will cover chapters 4, 5, and 6. So this is the first of that set. This will be the beginning of lecture test number 2 set of notes. So again, as we go through here, realize that 4, 5, and 6 will be on the second lecture test. So in our first slide here, we talked about, obviously, cells have to capture and use energy to power our muscles, to power all living organisms. And it says, what is the definition of energy? That's the ability to do work or to move matter. So anything that's along those lines, energy-wise, is again costly on us, and we have to expend energy to do movements. And again, move around a little bit, you burn a little bit, move around a lot, you burn a whole lot. So simplistic in that form that whatever we do requires energy, and the more we do, the more energy is required. Now, energy exists in a couple of different forms at its basis. There's potential energy and kinetic energy. Potential energy is stored energy, meaning like this bike rider on top of the hill. That energy is stored there and waiting to be released. Kinetic energy is energy of motion. By the time that bike rider gets to the end down here, they've released that energy in form of kinetic energy. So light, sound, movements, all of that would be kinetic energy. And energy changes forms within the biological system. We cannot create nor destroy energy. So energy is all around us. And again, it just transfers forms. I was talking in my live class that it sounds a lot like Star Wars. The Force is all around you, and obviously Darth Vader and Luke Skywalker are able to manipulate the Force to move things around. But again, one of the laws of thermodynamics, energy is not created nor destroyed. It only changes forms. Now, heat energy that's released every time forms are changed between such as sunlight, kinetic energy going into leaves to turn into cellulose, to turn into food for the deer, heat energy is being lost. We lose heat, again, through the process of respiration. Heat is disordered and cannot be reconverted back into a useful form. It gets re-radiated back into the atmosphere. So again, that leads to what is called entropy. And entropy is a measure of the randomness or disorder of the universe. Since heat energy is constantly being lost to the universe and the heat energy is disordered, entropy of the universe is increasing. So if you feel like your life is getting more chaotic, more disorderly, rest in the fact that the universe is actually becoming more disordered as well, because that heat energy is disordered. And for us, we talk about obviously burning energy, and that's true. That's a part of our metabolism. And metabolism includes these energies that are released through catabolic reactions. Catabolic, C-A-T-A-B-O-L-I-C, catabolic reactions that turn energy out. But it also includes building things as well, building molecules. Those are anabolic, A-N-A-B-O-L-I-C, anabolic reactions. Now, again, when people talk about metabolism, we often think in terms of catabolism and the fact that you burn it, and you've probably heard before the saying, oh, they have a high metabolism. They can burn up a lot of food. Well, that's true. Okay, high metabolism is catabolic reactions, but realize it also includes anabolic reactions. So your body is very good at building things up and then tearing them down. And we can see in this slide here that chemical reactions either require energy or they release energy. So energy requiring reactions such as photosynthesis, energy is put in. So analogy to that would be the barn raising we see here. All that energy is going into raising this barn and putting it together. And energy is required to make this assembly happen. So again, this is photosynthesis, which again, we have our own chapter about photosynthesis. And then we have a separate chapter for respiration, which again is the tearing down of what was built there. Notice too on the chemical formulation for photosynthesis, what goes in versus what comes out, your reactants versus your product. It's just turned around here. They just flip-flop. What you build with here results in this. We take the results here and then it results in this. So it's just flip-flopped, the opposites of each other. Now, most energy transformations in organisms occur in oxidation reduction reactions. Oxidation is the loss of electrons from an atom or molecule, and these release energy. Reduction is the gain of electrons and whatever energy is contained in them, and it requires energy. Now, I'm going to point this out to you. This is really a struggle for a lot of my students. Reduction is the gain of electrons. That is opposite of what you would think. Just remember, in science, when you reduce something, you're gaining an electron. So oxidation, losing electrons; reduction, gaining electrons. Just opposite of what you would normally think. And you see it here. Again, we'll talk about these reactions as these electrons move through this cell membrane here. These are protein channels, again, that are cleaned up for you to see, as we talked about in previous chapters. Proteins are nasty looking little things, are all over the place. So we clean it up so it's not as busy. But again, that's where energy is released at, in these little electron transport chains. And this electron transport chains, as it says, is just a sequential oxidation reduction reaction. Oxidation reduction reactions known as redox reactions, REDOX. You'll talk about that in quite a bit in chemistry. Redox reactions basically means if somebody's leaving somewhere, it's going to somewhere else. So if I had an electron and I threw it to Jason, Jason in that way would reduce and I would oxidize. Jason in turn throws it to Hannah, Jason would oxidize, Hannah will reduce, because remember, reduction means to gain. Reduction means to gain an electron. So the cellular currency that the body deals in, that kind of stores this energy for us, is adenosine triphosphate, ATP. And that bond here that glues this little phosphate group on here, the third one, this is what's going to get cleaved, split in two, to release that energy. Putting that on there requires energy. Splitting it releases energy. So at the cellular level, this is a little battery system that powers everything. ATP, adenosine triphosphate, adenine, which again is a nucleotide, and then ribose sugar. And then there's the tails of the phosphorus there. So like we talked about in previous chapters, if I want to break something apart, I add water. Hydrolysis breaks this tail loose, releases energy. And the cell can use it to do work and move things around. Now, once that energy is released, instead of ATP, you now have ADP. And we have to reform ADP with another phosphate to fuel the system, if you will. So again, you eat energy bars, you eat food to make this gluing back together happen. Now, plants make their own food through photosynthesis. You, on the other hand, have to eat things. You're a heterotroph. So again, you glue it back together and then water breaks it apart, and there you go, bicycling out across there. Water, a really overlooked component for energy. People run down, they think I've got to eat, and that's true. I got to have some energy from something, that's true. But water is what makes this split take place, that releases that energy. If you don't drink enough water, you're not going to be able to release the energy that you need from your food. So again, when energy is stored, that is creation of ATP. When we release energy, add water, okay, that's spending ATP. So again, take water out, we put it together, add water, we create energy. So ATP hydrolysis is coupled with energy requiring reactions. So as we glue ATP, using ATP to glue together like glucose here, 2 molecules of glucose, that creates ADP, and it also adds a phosphate to each of these groups that has attached itself now as part of that binding process of creating polysaccharides, these multiple chains of carbohydrates like we talked about in a previous chapter. Phosphate groups changes shape and the membrane that's needing to move things in and out. So sodium potassium pumps are very important for cellular health. They are very important, especially for those of you that are going to nursing. You'll hear about sodium potassium a lot, maintaining those levels to stay functioning properly. And sometimes that ATP has to add a phosphate here to bump this, to kick this stuff out through that process of active transport. And we'll talk about active transport later on, but basically it's shoving things out against a concentration gradient. So ATP allows that to happen as well. So it does a lot of work inside the body. Now, chemical reactions in the cells must occur very quickly to sustain life. We needed this thing to happen in a fairly quick amount of time because obviously, we don't want to spend a lot of time having these conversions done. And there's a lot of times that, we are in a situation where they don't occur as quickly. We'll talk about some of those as we go along here. So to speed the process up, we have enzymes, and enzymes are basically proteins that speed up chemical reactions. They're a catalyst. Catalyst means something that facilitates a reaction. So in this case, you see a substrate, which is a product you start with, and in the active site here would fit the substrate. This enzyme speeds apart the process of breaking down this substrate into products, the result of this reaction. So, one of the things that we have are in our bodies are enzymes, and a myriad of enzymes that are usually proteins. Digestive enzymes, your saliva has digestive enzymes. As soon as you eat food, this process begins. But there's also cardiac enzymes, there's liver enzymes that function to speed up reactions. In fact, if you have an episode where maybe they think you're having a heart attack, they're going to look at your heart enzymes at the hospital to see if there was elevated levels of that, because that is indicative of having a cardiac issue. So again, a lot of enzymes, and note, not all of these enzymes break down things. Some enzymes put things together and glue them together. So you've got those that tear apart, kind of that catabolism, catabolic reaction, and then some that glue it together, and that would be an anabolic reaction, building things. So an enzyme, as it says here, speeds us up by reducing the amount of energy needed. So by reducing the amount of energy needed, that means that they're going to save energy. Your body is really good at conserving energy because, again, it developed in a time when energy was kind of hard to find. We couldn't always run down to McDonald's or down here to Burger King or wherever and find a quick source of energy. That was only in the recent advent that we're able to find food on demand. And in a lot of parts of the world, they're still not able to do that. So our body does really good at conserving energy. And it says only some chemical reactions are occurring in a cell at a given time. How does a cell control the rate of these chemical reactions? Well, basically it's the enzyme and the substrate will change shapes here to prevent that substrate from turning into a product. So basically, let's say that you're eating, and let's say the substrate sugar. After a while, something is going to block it, and it says, okay, I don't need any more energy release out of this. I want this just to go away. There is what's called an inhibitor, which blocks or changes the shape here of the enzymes. If it changes the shape of the enzyme, it's called non-competitive inhibition. If it actually blocks it, that's called competitive inhibition. So if you're any soccer players out there, think about a goalie that's inside the goal there for a soccer ball, and then that soccer ball in this case would be a piece of chocolate comes in. I don't want to convert it to sugar. Okay, this thing is going to block it and kick it back out. Here, I've just changed the shape of it where it can no longer fit in that. This is a process called negative feedback, where the product of a reaction slows the production of more product. So again, you keep eating, chocolate, something like that, and the body says, no more sugar. This thing is going to break off and not be able to fit into that active site here. So the active site is where this reaction occurs, and that's how your body regulates it. Now, enzymes, again, have a preferred temperature at which they like to react in. Remember, for your body, all enzymes are around 98.6, 98.7 body temperature. That's where we do best at. Now, if it's an enzyme from a bacteria that lives in a hot spring, obviously it prefers much warmer temperatures. That's its natural habitat. So, when you get a fever, something along those lines, your body is fighting off an infection. You always feel sluggish and tired. Remember, if you elevate from your normal temperature, okay, that's going to slow the reaction times down, and you're going to be tired because of that. Or if you get really cold, you're really chilled, that slows the reaction times as well. Along with that, temperature, salt concentrations, and pH also affect enzyme activity. Had an uncle who had a liver transplant, had to quit eating tomatoes because the tomatoes have as we saw in a previous class, a low pH, and that affected his liver enzymes from his donated liver he had received. But again, these things staying in balance, salt, pH, temperature, affect our body. And when we don't keep it in balance, we can have some goofy things happen. Now, things come in and out of cells by a myriad of different ways, and we're going to look at some of those ways. But a lot of things are driven by concentration gradients, from high concentration to a low concentration. These solutes, these solutions, move across our cell membranes, again, in a variety of ways. Solutes just means that it's probably not pure water. It's got something mixed in with it. So when you hear the word solution, usually means a mixture of things. And depending on the size of it, the charge of it, things like that, there are different ways the cell can get things inside of it. So this concentration gradient, again, would be from a high concentration to a low concentration. So black pixels to low pixel concentrations. So as we look at it here, these next series of photos are going to show us some concentration gradients. So basically, Mother Nature does not like high and low concentrations. It wants to reach an equilibrium. So a lot of times, as we look at these, if there's one on one side and not a lot on another one here, they're going to filter out until a balance is reached. Now that balance, again, requires energy to maintain it at that. So once this concentration gradient has passed or dissipated, that concentration of in this case, ping pong balls is actually going to run to one side or the other. So it takes energy to keep them separated out, and it requires energy to make this separation happen. And again, that energy is given by ATP and the splitting of that phosphate group to provide that energy. So these processes, as I said, there's several ways in which they can move things around. The first three are passive transport, simple diffusion, facilitated diffusion, osmosis. Then we have active transport and endocytosis and exocytosis. We'll talk about each one. So passive transport, the first one, simple diffusion, is where you have a substance move across the membrane from a high to low concentration. Okay, it can move straight across. There are no barriers to it. Now, again, there's very few things that can do that because you have to have the right polarity, you have the right charge, the right size, things like that. That's simple diffusion. A good example of simple diffusion would be placing a coffee or tea bag into water, and you see the high concentration here, and then after a while, that concentration goes from high to low and it disperses throughout. Osmosis, same thing, diffusion of high to low concentration, except in this case, refers to water, from high to low in terms of water. So if you have a solution such as salt, okay, salt water, the water molecules are going to disperse over here until they bleed across and come and reach this equilibrium. Now, this is important for our blood cells because, again, our cellular components are activated and flow between these three stages. So the first we'll look at is an isotonic solution. Isotonic solutions have an equal amount of water inside and outside. So a solution, again, when you see that word, I tend to think of it as a salt solution. When the salt and the water are balanced, you're an isotonic, and that's what cells like. Hypotonic, cell swells up, becomes big. That's when you have more salt inside the cell, more solution inside the cell, and it sucks water into it and swells. In school, they taught us hypo and hippo. Okay, hypo, hippo, they're both big and round. And then the third one here, hypertonic. This is where, again, more salt on the outside sucks the water away from the cell, and hyper, children run out and play. All the water runs out. Okay, so this is ideal. These two, not so much. But again, you see the effects of salt and water, those solutions mixing together. I always tell my classes, remember one thing, salt sucks water. Wherever salt is, that's where the water is going. You know, when you eat a lot of salty food like popcorn or, you know, something like that, catfish with a lot of cornmeal, you're going to become thirsty because your body wants fluids to diffuse that amount of salt. Facilitated diffusion. This is passive transport again that requires membrane proteins. So in this case, we have a membrane protein that these little molecules slide through. Again, doesn't take energy to happen, but you got to have this little bridge, this little protein to come across. And again, we've cleaned it up for you here. It's a nasty looking little, you know, backlash is what it looks like. It looks like a bird nest in here, but this is how it works. And again, salt can work in this way because it's a polar substance, and you know the charges are different, and the tails will repel some of it, so it can go through that membrane channel that way. Active transport, and again, this is where you're going against the grain. So ATP in this case is needed to shove this guy out through that membrane channel here, that protein, and into the outside. I compare this to, again, we've got some cats, dogs, things like that. In the mornings, I'm trying to get our little Chihuahua outside the door, and every cat's trying to run in the house. So I'm actively using energy to get him out and try to keep the cats from running back in. It's a great analogy for active transport. A lot of it on one side, but I still got to get it out there, so I have to use energy. And again, you can see here that sodium potassium pump requires energy to make that happen. A very important process for their body, keeping these levels in balance. So even though it doesn't naturally want to flow that way, I've got to get it out, and that's how I do it, is through active transport. And then, if all else fails, there's endocytosis. And let's say there's some molecules out here that are very large, that can't come across, too big for transport protein, all that. Basically, the cell membrane will engulf those molecules and bring them in a vesicle. And again, vesicles are transport systems. We talked about that with proteins in the last chapter, moving proteins around. Vesicle that has this membrane around it that can move it in. So it engulfs it. Kind of like what we talked about with mitochondria and the chloroplast, that it probably is somewhere along the lines, those cells just engulfed those things and brought them in and started coding for them. Exocytosis, just the opposite. I got it in here, it's too big to get across. I make a vesicle around it, and basically the cell spits it out, okay, and releases it to the outside. So again, very resourceful the cells are in bringing things in and out in a variety of ways. Here's a little chart, again, might be good to study with or use on your test. Since it is an open note exam, you can use that to go through there and again, kind of a step-by-step guide of how it can move things out in each situation. The last slides, again, are always some of these did you know? And this one talks about cystic fibrosis. Cystic fibrosis, again, is a terrible disease. It actually leads to the watery fluids and mucous membranes being thickened. People that have this, don't have slippery mucus like we have. And again, it affects not only airways, but digestive system, reproductive system, all organs throughout the body. I've had students before that have had family members that have had cystic fibrosis. A lot of times it leads to shortened lifespans because of it, the damage that this thing does. And they know what causes the problem. It's actually a malfunction in the CFTR proteins, and it makes breathing very difficult. In contrast, cholera toxins overstimulate CFTR proteins, resulting in watery diarrhea and severe dehydration. So cholera is, again, a toxin that will affect the body. We don't see cholera outbreaks in the developed world anymore. Still see it in some third world countries. But again, cholera used to be a large killer of people. And again, a very nasty thing in its own right, which is the exact opposite of cystic fibrosis. And what they found was that the faulty CFTR proteins that cause cystic fibrosis might be maintained in a population by protecting against cholera. So places where you have cholera outbreaks, that people that have this CFTR protein issue are actually able to hold off the effects of cholera. And that is, again, an example of natural selection in process. And you think about these diseases that are inherited, like cystic fibrosis, you think, why would that stay around? I mean, it's such a bad disease. Well, actually, against cholera, it has a reason for being there. So again, it's a terrible disease. Both of them are terrible diseases, but one counteracts the effects of the other. There's also a book and a movie called Love in the Time of Cholera. Because nothing says love quite like watery diarrhea and severe dehydration. But again, we'll talk more about cystic fibrosis as we go along and the inherited patterns of this when we get into genetics. But this is interesting because, again, this is an example of a disease that's allowed to stay around in our population just because it protects against a toxin here such as cholera. And that is the end of our chapter 3 notes, or excuse me, chapter 3. I'm still last week. Chapter 4 notes. Chapter 5 will be coming up.